One last application of the binomial theorem is in the pejoratively named freshman's dream. And what the freshman's dream says is that if you were to take x plus y to the p, this is congruent to x to the p plus y to the p mod p. Okay, so this is very silly, and it's named a freshman's dream. But the idea is that when you ask a freshman, what's x plus y squared, oftentimes I say x squared plus y squared. And it turns out that that's true if you're working mod 2. So x plus y to the p is congruent to x to the p plus y to the p mod p. What I want to do to prove this, so let's prove this. So for a prime p, let me say this nicely, for a prime p, and for integers x and y, we have x plus y to the p is congruent to x to the p plus y to the p mod p. So the way that we're going to analyze this with the proof is I want to look at this quantity x plus y to the p. That's binomial theorem right down the middle. So we're going to look at the term x plus y to the p. By the binomial theorem, we have that x plus y to the p is going to be the sum as k goes from 0 to n. I'm sorry, from 0 to p of p choose k, x to the k, y to the p minus k. And what I'm going to do is I'm going to peel off the k equals 0 and k equals p terms for reasons that we'll make clear soon. But when k is equal to p, you end up with p choose p, x to the p, y to the 0. When k is equal to 0, you end up with p choose 0, x to the 0, y to the p, plus the rest of it. So the sum from k equals 1 to p minus 1, p choose k, x to the k, y to the p minus k. And of course, the first two terms are x to the p plus y to the p. But the last term is what I want to look at. So this is going to be k equals 1 to p minus 1, p choose k, x to the k, y to the n minus k. Now, notice that if k is between 0, if k is between 1 and p minus 1, in other words, if k is greater than 0 and strictly less than p, then p divides p choose k, since p choose k is nothing more than, so p choose k is nothing more than p factorial over p minus k factorial times k factorial. And the only way, remember that primes specifically have that property that the only divisors are themselves and ones. The only way that you could cancel this prime up top is if you had a prime down below. And that can only happen when this term has a p in it, which happens when k is 0, but we've eliminated that because k is starting at 1. Or when this term has a p in it, which happens when k is p, but we've also eliminated that. So it turns out that in this case, since k is in this range, since k is between 1 and p minus 1, then of course k is in this range. I'm rewriting. This is a circular argument. It sounds kind of silly. And p minus k is in that range. So if you were to look at p minus k, you would end up with p minus k will be smallest when k is largest. So if k is p minus 1 and you take p minus that, you're going to end up with 1. And likewise, if k is 1 and you take p minus that, you'll end up with p minus 1. So since k and p minus 1, k and p minus k are in this range, that means that they can never be p themselves, and therefore this prime up in the numerator is going to be stuck there. So it turns out that this is going to be a multiple of p for k in this range. And the reason why this matters is it matters, therefore, that x plus y to the p is going to be congruent to x to the p plus y to the p plus the sum, because they're equal. So since they're equal, they're congruent. So x to the k, y to the p minus k. This should be a p minus k. Mod p. So since they're equal, they're definitely congruent with whatever modulus. In this case, we're working mod p. But since k is in this range that it is, k goes from 1 to p minus 1, it turns out that this p choose k is a multiple of p. So therefore, this is going to be 0 mod p, and that gives us our result, that x plus y to the p must be congruent to x to the p plus y to the p mod p. Okay, and so just think about if you were to draw Pascal's triangle for a second. You have 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. I'm going to draw up to the 7th row. Okay, so we have 1, 6, 15, 20, 15, 6, and 1, and then 1, 7, 21, 35, 35, 21, 7, and 1, of course, based on symmetry. But I'm just going to look at the prime rows. Okay, so I'm only going to worry about the prime row. So I'm going to look at 1, 2, 1, 1, 3, 1, 1, 5, 10, 10, 5, 1, and then the 1, 7 row. And notice that if I ignore, if we ignore the starting points, if we ignore the leading ones, and if we ignore the final ones, all of these other terms are going to be multiples of that corresponding prime. So of course, there's only one number here, and it's 2, so that's multiple of 2. There's 2 3s, those are both multiples of 3s, fine. But for the 5 row, 5 and 10 are both multiples of 5. And I think for the 7 row, it's even more apparent that the 7, 21, 35 are all multiples of 7. Okay, so this is really what we're saying here is that if p is a prime, and if you pick the binomial coefficients where you're avoiding having a p in the denominator, then the p is stuck in the numerator because there's no choice. P is only divisible by itself, and we said it's not in the denominator. Therefore, this is going to be a multiple of p, so it's congruent to 0 mod p. So that's basically the argument. And again, this is called, oops, this is called the Freshman stream.